In this first part of Chapter 8, we'll cover the concepts of risk and return and how they're measured for individual assets on a standalone basis. Investment risk has two dimensions: standalone risk, the risk of holding an asset in isolation, and portfolio risk, the risk of holding an asset as part of an investment portfolio. When we talk about investment risk, we're concerned with the possibility that the return on an investment will be less than what is expected. More is great, less is not. Think back to your basic statistics class in the Algebra and Statistics Review lesson, probability distributions. A probability distribution lists all possible outcomes and the probability of each outcome occurring. The slide graphically displays two probability distributions, one for firm X, one for firm Y. Firm Y is riskier than X. There's a higher probability of a lower than expected return. The graph also visually demonstrates that the wider the distribution, the riskier the asset. Let's look at a set of hypothetical investment choices. First, the states of the economy and the probabilities of each state occurring. Next, the expected return on a treasury bill in each state. Since a T-bill is basically risk-free, the expected return is the same in every state. The market portfolio is a theoretical construct meant to represent all traded assets. The S&P 500 is typically used as a proxy for the market portfolio. And finally, our two sample assets, high-tech and collections, and we'll be using them in our examples in this lesson. High-tech is a fairly typical asset. Its return pattern matches the states of the economy. That is considered a cyclical investment since its performance follows the business cycles and is positively correlated with the market overall. Collections, on the other hand, is counter-cyclical. As a collection agency, it does well when the economy is in a recession, poorly when the economy booms. It's very unusual to find a stock that performs like this, one negatively correlated with the market. To begin, we need to be able to use a probability distribution to find the expected rate of return on an asset. The formula on the slide is a standard weighted average with the probability as the weights. Following the basic weighted average solution technique, you multiply across and add down. R hat is the total expected return on the asset. RI hat is the expected return on the asset in the ith state of the economy. P sub I is the probability of that ith state occurring. Sigma is the summation sign. It sums items from 1 to n. And we'll look at an example on the next slide. Given the data on the states of the economy and the expected return for high-tech under each state, multiply across each probability times each expected return, sum the results to find the expected return for high-tech, 9.9%. Repeating the calculations for each asset in the sample, the results are shown on the slide. High-tech has the highest expected return. Expected means expected by you. The catch, we haven't accounted for risk. Risk in finance is measured by the standard deviation of returns. Remember our look at the graph of a probability distribution? Wider is riskier. That's what standard deviation measures, the spread of returns. The use of standard deviation is based on a basic assumption in finance that the returns on a stock are normally distributed. This is a strong, yet empirically supported assumption. It allows us to analyze returns using parametric techniques, which are more robust than non-parametric methods. It also implies that we can describe the distribution of returns by the mean and the variance. But the problem with variance is that if returns are measured in percentages, then the metric for variance is percent squared. Not very useful. But standard deviation, the square root of variance, is measured in percentage, like expected return, and is more intuitively comfortable. This formula is for the standard deviation of returns from data presented as a probability distribution, expectational data, not historical. Using T-bills as an example, not a great choice since Treasury bills have no risk. This is the case where order of operations is critical. PEMDAS. What's inside the parens, exponents, multiply, divide, add, subtract. We'll work through an example step by step. Given the probability distribution, Find the expected return. It's a weighted average. Multiply across and add down. We find the expected return as found earlier, 9.9%. With the standard deviation, start with what is inside the parentheses, the deviations. Each state's expected return minus the overall expected return. Then handle the exponent. Square the deviations. Then multiply those values by the probabilities. Finally, add all those up to find the variance. And last, take the square root. This process was covered step by step in the video tutorial in one of the first lessons, Algebra and Statistics Review, and is available again with this lesson for review. If you feel you need to review the steps involved in finding standard deviation, take the time to watch the video tutorial again. Standard deviation, lowercase sigma, measures total or standalone risk. The larger the standard deviation, the lower the probability that actual returns will be close to expected returns. The larger standard deviation is associated with a wider probability distribution of returns. Comparing the standard deviations of the Treasury bill, high-tech, and U.S. rubber graphically. The T-bill curve is a vertical line since it has no deviation. U.S. rubber is to the left of high-tech but is slightly more arched, implying a tighter distribution. Here we have the expected returns and the standard deviation for all assets in our sample group. Treasury bills, 3% return, 0 risk. High-tech, 9.9% return, 20% risk. Collections, 1.2% return, 11.2% risk. U.S. rubber, 7.3% return, 18.8% risk. And the market, 8% return, 15.2% risk. Expected is expected by you. So how do you choose which asset to invest in? None have the same expected return or the same risk. The solution is the coefficient of variation. Standard deviation divided by expected return. It's risk per unit of return. Lower is better. The coefficient of variation allows us to choose one asset to hold in isolation from a group of assets. Here's a graphical representation of why we need the coefficient of variation. A and B have the same standard deviation, but A is clearly riskier than B. More of its possible returns are negative. Here are the coefficients of variation for all of our sample assets. Collections has a very high CV, low return, high risk. High-tech, which had the highest risk metric, is really only slightly riskier than the market. The Sharpe ratio is an alternative measure of standalone risk. It looks at excess return relative to risk. Excess return is an asset's return minus the risk-free rate. Risk is measured as the standard deviation of the asset's return. A risk-free asset will have a Sharpe ratio of 0. Investments with higher Sharpe ratios tend to perform better. High-tech. The risk premium is the difference between the return on a risky asset and the risk-free rate. It's the compensation to entice investors to hold risky assets. The risk of an investment is important because the average investor is risk-averse, meaning to take on more risk, he demands a higher reward. This ends Part A of Chapter 8.